Antarctica is supposed to be a frozen desert, right? A vast, static continent of ice, locked in a deep freeze for millions of years. It's the coldest, driest, and highest continent on Earth, a place defined by its seemingly endless ice sheet. But that image of a simple solid block of ice is profoundly misleading. Because beneath that serene, frozen surface lies a world of unimaginable complexity and dynamism. Turns out, it's also a secret water park, buried under kilometers of ice. This isn't just a handful of isolated ponds. We're talking about a sprawling, interconnected network of hundreds of liquid water lakes, hidden from sight, some as large as a major city. This is Antarctica's subglacial hydrosphere, a hidden plumbing system that fundamentally changes how we understand this continent. For years, we could only guess at the full extent of this hidden world. But now, using a decade of data from the European Space Agency's Cryosat-2 satellite, we have a revolutionary new view. Cryosat-2 is an ice monitoring mission, but it doesn't see through the ice directly. Instead, it uses a sophisticated radar altimeter. Think of it like a hyper-accurate tape measure in space. The satellite sends down a radar pulse, which bounces off the surface of the ice sheet and returns. By measuring the time it takes for that signal to travel, scientists can calculate the precise height of the ice surface down to a few centimeters. By repeatedly mapping the same areas over 10 years, they can spot subtle changes in this elevation. When a subglacial lake fills with water, the immense volume pushes up on the kilometers of ice above it, causing the surface to rise, sometimes by several meters. Conversely, when a lake drains, the ice surface above it subsides. These subtle movements, invisible to the naked eye, are clear signals to the satellite. By tracking these ups and downs across the entire continent, scientists can map the activity of the water hidden below. And the results of this decade-long survey are staggering. Scientists just mapped 85 previously unknown active subglacial lakes. This discovery nearly doubles the number of known active lakes, bringing the total to 169. It reveals that this subglacial water system is far more widespread and dynamic than we ever imagined. And these lakes are active, as in they fill and drain slowly under the ice. This isn't a rapid flush. It's a ponderous, powerful process. The immense pressure from the overlying ice sheet keeps the water liquid, even at temperatures below freezing. They even caught 12 complete fill-drain cycles, watching from space as these hidden reservoirs swelled and then emptied over months or years. This gives us an unprecedented look at the pulse of the continent's hidden heart. And they found 5 lake networks, intricate systems where multiple lakes are connected by subglacial rivers and channels. In these networks, the behavior of one lake directly impacts another. They observed a fascinating phenomenon where water drains upstream and fills downstream, like a slow-motion cascade beneath a continent. One lake empties, and its water is forced through a hidden channel to fill the next lake in the chain, which then might overfill and trigger a drainage event further down the line. It's a chain reaction, propagating for hundreds of kilometers under the ice. Why does that matter? Why should we care about water moving around deep beneath a polar ice cap? Because water under ice works like oil on gears. It's a lubricant. This water doesn't just stay in the lakes. As it moves, it spreads out, creating a thin film at the base of the ice sheet. This meltwater comes from 2 main sources. First, geothermal heat. The Earth itself is warm, and that heat radiates up from the planet's core, slowly melting the very bottom of the ice sheet. The second source is sliding friction. Ice sheets are not static. They are rivers of ice, flowing under their own immense weight. As this ice grinds over the bedrock below, the friction generates heat, just like rubbing your hands together. This heat melts more ice, adding to the water at the base. This combination of geothermal heat and friction can reduce drag between the ice and the bedrock, letting ice slip faster toward the ocean. The more water there is, the slipperier the bed becomes, and the faster the ice can flow. These subglacial lake drainage events can release huge pulses of water, lubricating vast areas of the ice sheet bed and causing sudden accelerations in ice flow. And here's the kicker. Most sea level rise models don't include this subglacial plumbing yet. Our predictions for how fast Antarctica's ice will melt and contribute to rising oceans are based on models that treat the continent's base as relatively simple. They don't fully account for these complex dynamic networks of lakes and rivers. This hidden water system can have a major impact on the grounding line, the critical point where the ice sheet lifts off the bedrock and begins to float as an ice shelf. Faster flowing ice can push this grounding line further out to sea, while pulses of meltwater can lubricate the bed right up to this point, destabilizing it. Understanding this plumbing is essential for accurately predicting the future of the ice sheet. So to predict the future, I need to understand what's happening where no one can see. We need to get beneath the ice. Now, jump to Lake Enigma, an Antarctic lake once thought to be solid top to bottom. Located in the McMurdo Dry Valleys, one of the few ice-free regions of the continent, this lake was considered a relic, frozen solid for millennia. Radar said otherwise. Ground-penetrating radar surveys hinted at something strange, a layer deep within the lake that was reflecting the signal in a way that solid ice shouldn't. It suggested the presence of liquid. To find out for sure, a team of scientists went in. They used a specialized hot water drill to melt a borehole through the ice. Drills confirmed it, about 14 meters of ice sealing at least 12 meters of liquid water. A hidden, hypersaline brine, so salty it remains liquid at temperatures far below freezing. They had punched through into a lost world. Cameras revealed the bottom carpeted in microbial mats, thick, layered communities of microorganisms. This wasn't a barren, sterile environment. It was teeming with life. Some of these mats were forming incredible tree-like structures, up to 40 centimeters tall, reaching up into the dark water. And they were huge, with some individual structures measuring 50 to 60 centimeters across. These are ancient, slow-growing biological structures, built layer by layer over countless generations. The stars down there? Ultra-small Ptacibacteria, a mysterious and poorly understood group of microbes, sometimes called microbial dark matter. And they were dominant in a place where they'd never been seen in an ice-covered lake before. These bacteria are known for their tiny genomes and limited metabolic capabilities, suggesting they rely on other microbes to survive. And the community is incredibly complex. There are photosynthesizers, like cyanobacteria, which somehow manage to eke out an existence with the faint light that filters through the ice. There are partners living on partners, with different species forming symbiotic relationships to survive in the nutrient-poor water. There are even predators, microbes that hunt and consume other microbes. It's a fully fledged ecosystem with all the roles you'd expect in a sunlit pond, not an ice-locked vault that has been sealed off from the outside world for thousands of years. And this ecosystem may have persisted for roughly 14 million years. Analysis of the sediments and the life within them suggests this lake has been a stable, liquid environment for an immense span of geological time. It's a living time capsule from a warmer Earth, sealed and ticking. It contains clues about how life can persist in extreme isolation and what Antarctica was like long before the ice sheets grew to their current extent. And here's the cosmic twist. Environments like this might exist on icy moons in our own solar system. Moons like Jupiter's Europa or Saturn's Enceladus, where we know vast oceans of liquid water hide under thick shells of ice. These moons are considered some of the most promising places to search for extraterrestrial life. The same physics are at play. Just as geothermal heat and friction warm the base of Antarctica's ice, the gravitational pull of giant planets like Jupiter and Saturn constantly squeezes and stretches their moons, generating tidal friction that heats their interiors and maintains liquid oceans. Antarctica's subglacial lakes are our most accessible analog for these alien oceans. by learning how to drill through kilometers of ice without contaminating the environment below, and by studying the unique life that survives there. We are essentially rehearsing for future missions to explore these distant worlds. The life in Lake Enigma could be a template for what we might find. So when I study Antarctica's hidden lakes, I get a window into two of the most critical questions of our time. One looking at Earth's future sea level, and the other looking outward, giving us a preview of the potential for life beyond Earth. Beneath the quiet ice, everything's moving. Water is flowing, ice is sliding, and life is persisting against all odds. Each new discovery in this hidden realm is rewriting what I thought I knew about our own planet and what might be possible on others.